It's a pleasure to introduce our last speaker, Professor Giancarlo Lucchini Arteche from Universidad de Chile. He will talk about local global principles for homogeneous spaces over geometric fields. Please.
Thank you very much, Adrian, for the presentation, and thankful to the organizers for the invitation to give a talk here. I do realize that I'm a little bit of an outsider in this group. Even though there's a lot of algebraic groups and a lot of number theory in what I do, there's actually few connections to the world of representation theory or the world of automorphic or modular forms in general. So what I want to do today is present you the whole field of these weird geometric fields I'm going to talk about that has been occupying a whole bunch of people actually in the late years. Okay, so in order to do this, let me start with the classical setting. So let me tell you a little story about the classical situation. So number fields, real number theory. Okay, so first of all, I'm going to talk about number fields and present the classical problems in this area. And then, oh, sorry. Having a problem here. I don't know why I can't erase. Anyway, there you go. And later on, I'm going to talk about these weird geometric fields, okay? This is joint work with Diego Izquierdo, but as I told you, I'd rather present the subject and then the actual results with Izquierdo. I'll present them by the very end of the talk. And yeah, I put this geometric here in accolades because yeah, I actually asked Diego later, like what he thought about these name geometric fields, and he told me, yeah, you should not call them that way. So, but I had already sent the title, so yeah, I shouldn't call them geometric fields. But the idea is that these are fields that behave like global fields, and they come from a more geometric construction, classic objects that one might consider in algebraic geometry. Okay. So anyway, number fields first. So let me fix notations. K will be a number field here for the whole first part. So omega will be the set of places, right? Places of K. And if I take a V in omega, of course, I can write KV for the completion, as you would imagine. So a p-adic field. In general, X will be a K variety. Soon enough, it will be a homogeneous space, but in general, it can be an K variety. So I can consider the set of adelic points, okay? So these are adelic points in the variety. And of course, these can be seen as a subset of the product of the KV points for V in omega, okay? And actually, if you take a projective variety, these two coincide. So if you don't know what adelic points are, just think about these. This is easier to think about. So anyway, let me remind you, probably you all know this, but anyway, what the local global principle is all about. So here I'm concerned in local global principles for existence of rational points. So the classic has principle, okay? So this I'm going to call LGP. And it asks the following, whether if I have an adelic point, which is essentially equivalent to having a point on each completion of the field K, then I do get an actual rational point on the variety. So this is what Minkowski proved for over Q for quadrics, so just one equation, quadratic equation, and Hasse generalized that for quadrics over any number field. And that's the first result in this sense. Then already in the 30s, there were counterexamples that were found. The nicest counterexamples were found, for instance, by Selmer in the 50s, where you get a cubic curve, just 3x cubed plus 4. So for instance, this one, 3x cubed plus 4y cubed plus 5z cubed is just a plain curve. And this has points locally everywhere and has no rational point. So this is a counterexample to the local global principle. But okay, so there were lots of counterexamples appearing in the 30s, 40s, 50s. And at some point, Manin in the 70s came up with an explanation for all this. So in the ICM of Nice in France in 1970 precisely, he explained that actually you can explain, once again, I'm having some problems with the undo button. anyway. I don't know why. So you can explain failures of the local global principle using what is called the Brauer-Manin obstruction. Okay, there you go, Brauer-Manin obstruction. Of course, Manin wasn't that selfish. He called it the Brauer obstruction. Nowadays, it's called the Brauer-Manin obstruction. So let me explain you a little bit what this Brauer-Manin obstruction is all about, because it's a nice obstruction that in the 70s actually explained every known counterexample. So since it's Brauer, it actually uses the Brauer group. So let me remind you what the Brauer group of a variety is. Well, by definition, it's just étale cohomology. You take the étale cohomology of X, second étale cohomology group with values in the multiplicative group. That's the Brauer group. Having this, you can get what is called the Brauer pairing, which is a quite natural pairing. Okay, yeah, I'm really sorry about the writing, but yeah, I'll try to do my best, but it's what you can do when you don't have a board. Anyway, okay, I'll try to write slower so that it's clearer. Anyway, so there's this Brauer pairing that takes, so for any field, and actually any ring over K, you can take an L point of X, and you can take a class in the Brauer group, and you get something in the Brauer group of L. How do you do this? It's quite simple, actually. Just take a point, take a class alpha, okay? The notation you use is just alpha evaluated at P. And it's actually somehow an evaluation, but since it's a étale cohomology, this is quite natural, actually. P in algebraic geometry is just a map from spec L, from the spectrum of L, to the variety X. So you're just pulling back the class on Brauer X to the Brauer of the spectrum of L, which is essentially Brauer L, okay? So it's just pullback. It's a quite natural map. But using this Brauer pairing, you can do the following. So now you fix an alpha in Brauer of X, okay? And so you can take adelic points and you can evaluate at alpha. Okay, so you're going to fall in the Brauer group of KV. A priori you fall in the product, but since you take adelic points, you can actually prove that you fall in the direct sum for V and omega. Okay, now inside here, you want to study, that's the point of the local global principle, the set of rational points that is contained in here diagonally. It's a natural conclusion. So here you can also evaluate at alpha, and you're going to fall in Brauer K. And since this thing is just pullbacks, well, this is quite natural. So you get an arrow here that makes the whole square commute, okay? And this map over here, if you recall your first lessons on class field theory, for instance, so every person here probably knows this, there's a map from Brauer K to the direct sum of the Brauer KVs that is actually injective, and we actually know the co-kernel is Q mod Z, okay? And this map over here is the sum of the local invariants, okay? So these are maps from Brauer of p-adic field to Q mod Z, that's essentially local class field theory. So you get this map, this whole drawing here, and you can now define the Brauer-Manin pairing. So this is by definition just the composition of these two arrows. So this is Bm of alpha in a given adelic point, okay? This is the Brauer-Manin pairing, okay? So how does this work? Well, the point is, if I take an adelic point and I evaluate it in alpha and then push via this arrow here, then I get some number in Q mod Z. But if the point actually came from a rational point, well, it should factor through here. And since this thing is a complex, I get 0. So rational points always give 0 via the Brauer-Manin pairing. So adelic points are not the important thing to study. What you want to study is adelic points that are orthogonal to the Brauer group via this pairing, okay? Okay. Oh yeah, I just have here in my notes, I just want to state the name of this sequence below, just to remind you, this is the Brauer-Hasse-Noether theorem. This exact sequence below is precisely the Brauer-Hasse-Noether theorem, which is going to come back afterwards. That's why I want to give the name. So anyway, That's the point of the obstruction. So let me be more precise now. So you define, as I said, you take the adelic points that are orthogonal to Brauer of X. So by definition, let me write down the definition. These are the points in, well, the adelic points, so the families of PVs in X of AK, such that, well, the Brauer-Manin pairing of alpha and PV gives 0 for every alpha in the Brauer group. Okay. So that's a definition of the so-called Brauer-Manin set. Okay. And by the way, let me just state here that you can actually define this set for any subset or subgroup of the Brauer group. You just change the Brauer X here by some B, and you can define it for suitable subgroups so that you can define actually weaker obstructions. Because if you take a smaller group here, you're taking a bigger subset of the adelic points. But sometimes it's nicer because some subgroups of the Brauer group are easier to control. So that's the set you want to look at. And what I just explained transforms into the following. So rational points are actually contained in this Brauer-Manin set, right? Which is a subset of the adelic points. So if the adelic points are non-empty, if you have rational points on every completion, but by some miracle you do not have adelic points that are orthogonal to the Brauer group, well, you get a failure of the local global principle. Okay. So yeah, that's essentially the Brauer-Manin obstruction. And once again, recall that this obstruction explained every known counterexample at the time Manin presented this obstruction. Nowadays, we know that there are varieties that have this set non-empty and they still do not have a rational point. The first examples appear at the end of the 90s, 99, maybe even 2000, I think, by Skorobogatov. But nowadays, there's a whole bunch of them. However, there is still an important conjecture by Collet-Helene that tells you that this should be the only obstruction. I'll give the precise definition of that immediately, but this should be the only obstruction for rationally connected varieties. Okay? If you don't know what a rationally connected variety is, never mind. The important thing is that homogeneous spaces are rationally connected varieties. So let's go to homogeneous spaces. So now G will be a, I'll try to write better, a connected linear K group, okay? And X will be a homogeneous space of G, okay? So this means that G acts on X and the action is transitive at the level of K bar points, okay? That's one way of defining this, at least in characteristic 0. Okay, so now let me state the conjecture by Collet-Helene, at least the part that concerns our topic, that is homogeneous spaces. Okay, so this is not the whole conjecture, this is just the implication of the conjecture in this context. But it tells you essentially that, yeah, if by any chance you find adelic points that are orthogonal to the Brauer group, then you do get a rational point. Okay, so this is essentially saying that the Brauer-Manin obstruction to the local global principle is the only obstruction. Okay. So now, to end the story in the case of, in the classical case, so let me tell you a little bit about what's been done with respect to this conjecture. I mean, there's a lot of things that we know, and there's a lot of things that we do not know. So let me give you the main milestones of this story. So first of all, the conjecture is okay if X is a principal homogeneous space. Okay, so that is a torsor. Okay, so this is a result by Saint-Sucre in 81. And so that another way of stating this is that there are no stabilizers. So stabilizers are trivial for the action, okay? And then, okay, so principal homogeneous space are great. What about non-trivial stabilizers? What about, for instance, connected stabilizers? When? Well, it's still okay. Okay, if X has connected, and actually I can change connected by a billion with no problem. So it could be disconnected as long as it is a billion stabilizers. So these are very important results by Borovo in the 90s. So the last one was in 96, if I'm not mistaken. So yeah, right, 96. So moreover, in these two cases, before I go on, moreover, in these two cases, actually one can use a particular subgroup of the Brauer group. You can use what are called the locally constant classes, okay? So let me define precisely what this is locally constant classes in Brauer X. So that is this Cyrillic B of X, defined as, well, the alphas in Brauer of X, such that, well, when you localize them, so you take alpha V, so this guy lives in the Brauer group of XV of on the base change to KV, right? And this guy, well, it actually comes from the base field. So you get a natural map from Brauer of KV to Brauer of XV. This is just a structural morphism, okay? You can draw it over here. So XV has a natural morphism to spec KV, right? And that gives you a map of Brauer groups on the other sense. So yeah, so you want your class to be coming from the constant, so from the base field, sorry, for every V in omega, okay? So I'm doing here an abuse, actually, for those who know, this is actually, I must quotient this subgroup by something else to actually get what we usually denote by this, but I don't want to get into technical details. So this definition works just as fine. It's just not the usual notation. Okay, so this is a nice group that is easy to compute a priori. It has a lot to do with the Tate-Shafarevich groups, as I will explain to you later. Anyway, let's go on with the story. So, okay, connected stabilizers are good. What about non-connected stabilizers? So the most typical example of a non-connected group would be a finite group. What about them? Well, as we proved with Demarche in last year, in 2019, it suffices actually to prove the conjecture for G equal SLN. So you do not need to look at any other linear group, just SLN, and X, a homogeneous space of SLN with finite stabilizers. So it's technically a conditional result, okay? So if you prove this case, then you got the whole conjecture. So it's a reduction theorem. You reduce the whole problem to this case. But it's actually more precise than that. You can, given a homogeneous space, you can build a precise homogeneous space of this kind for which you can answer the question directly. So it's a little bit more precise than that. But anyway, so this was Demarche and myself, 2019. And finally, of course, okay, so finite stabilizers, great. What about them then? Well, there's a huge result published this year by Harpas and Wittenberg that works for finite hyper-solvable stabilizers. Okay, so this is Harpas and Wittenberg. Actually, it got published this year. So hypersolvable is essentially solvable, but you gotta split, slice your group into cyclic groups, not just a billion, okay? So for instance, nilpotent groups would work. And this is a huge result, actually. If you apply this not to the local global principle, but actually to a really related property that is weak approximation, you get really, really, really strong versions of the inverse Galois problem for these guys. You get like global extensions with this Galois group that actually have local conditions and as many as you want. It's like really crazy results implied by this kind of theorem. So this is why I tell you this result here is quite huge. Okay. So anyway, that concludes the first part of the story. So this is what we know. This is what we have done in the classic setting. Okay. So now let me tell you about what people have been doing ever since, I don't know, last 5, maybe 10 years. So let me introduce you to these weird geometric global fields. Okay, so what is this? Oh, sorry. So I'm going to introduce 2 examples of what I'm going to call geometric global fields, but there's actually lots of them. And they have been tackled by many people. Let me just cite some names so that I do not forget anyone. So first of all, there's Kolyatlan himself, but not only him. There's Parimala, Suresh, Harbader, Hartman, Krashen, Harari, Samueli, Scheiderer, Izquierdo. Actually, yeah, I'm probably forgetting some, and I'm sorry if I do. But there's a whole bunch of people that have been working lately on these kinds of fields. So I'm just going to give 2 examples that are the ones that we have been working with Izquierdo. Okay, so the 2 examples, one is nice and one is less nice. So let me just define them as that. First, the nice case. And I call it the nice case because the analogy is quite evident, okay, with the classical case. So let's take small k to be C double bracket T. So this is the field of Laurent series over C, the complex numbers. Let's take C now a projective, smooth, well, nice curve. So geometrically integral curve, okay, over K. And then big K, the actual global field, will be just the field of functions of our curve C. Okay, so you see the analogy immediately. So you know that global fields over in current positive characteristic are just function fields of curves over a finite field. So I just changed the finite field by this weird guy over here, but arithmetically speaking, they are quite similar. The absolute Galois group of this field is precisely Z hat. It means that the only extensions that we have here are cyclic extensions, and there's 1 per each n, and that's essentially the same theory that we got for finite fields. So this should look a lot like global fields in positive characteristic. And it does. But of course, there are some differences. So let me show you a little bit the first difference. That is the following. We got 2 types of valuations here. So now this is the global field, so we want to complete it, so to get local fields, right? So there are 2 types of valuations of K. One you already guessed, okay? So the first one is the ones where V is trivial on K, on small k. Okay, these guys actually correspond geometrically to closed points in the curve. And this is precisely what we do in positive characteristic. But evaluation has to be trivial over a finite field. So that's all there is for finite fields. But now V can be non-trivial in this new context. It can be non-trivial on K, on small k. Actually, you can take this guy here has a natural evaluation, of course. And you can try to extend this to big K, and you get new evaluations on big K. So, and here you would like to have some geometrical object, right? And you don't know what to do. So let me try to explain you a little bit. How do you associate to these kinds of evaluations a geometrical object? Okay, so yeah, I'm going to change the page. So consider the following ring R is just the ring of power series in T. So the fractional field of this is, of course, small k, right? And you fix a model. I'm going to call it curly C over R of our curve C over K, right? So in a picture, it would look something like this. So this big fat point will be the generic point of R. So this would be a spec of K, right? Small k. Let me change color here. So you have a tiny point that would be the closed point that is essentially spec of C. And let me change color again. So I can put these two together, and that essentially is the spec of R, right? So now, over K, I get a curve, right? So this is my curve C. And when I fix a model, well, I get something weird over here. So I can get like really, really ugly stuff. For instance, I can get triple intersections, I can get, nodes or what have you. And this is what I'm going to call the closed fiber, of course. So let me just call it curly C0. Okay, that's just notation. And once again, so this whole thing over here would be our curly C. Okay, so that's pretty much the drawing. So you get an arrow over here, you get an arrow over there, and that's our model. So first things first, I mean, this can be really, really ugly. C can be singular in general. But yeah, of course, we are in characteristic 0, we're over C. So we can apply Hironaka's theorem. We got access to all these kind of tools. So you can actually desingularize. To get a nice C0, and what I mean by nice, I mean a strict normal crossings divisor. Okay, that's the best you can get, and that's actually all that you need. So I will assume from now on that this guy is not that ugly. There are no triple intersections. There are no nodes like this. It's just bunches of curves that intersect, but nicely. Okay. Okay, so now that I have this, well, I can take for each irreducible component of C0. Well, this is a divisor in curly C, right? And a divisor in curly C, well, this gives me a valuation in the function field. And the function field of curly C is just big K, our global field. Okay, so what we get there is a valuation in big K. And these are the new ones, actually. These are the ones that are non-trivial over this field over here, because they actually induce the valuation that is defining R somehow. Okay, so so I'm going to define now omega 0 as the whole set of new valuations. So the ones that I just defined, so valuations coming from C0, right? And I'm going to add all the other ones. Oh, I'm sorry, actually, I forgot to define. Let me go back here. So these guys, the close points in the curve, the classical valuations, I'm going to call this set omega to do the analogy with the number field case or with the global fields and positive characteristic. Okay, so this is omega. This is the small set of places. And now I'm defining the big set of places that is omega 0. That is just these new guys and omega. Okay, so I'm going to keep the notations here. So that's the nice case. Let us go now to the less nice case. So that I like to give at least 2 examples so that you see that there are more than one situation that one can consider, and one can treat them both at the same time with the same techniques. Okay. So now the less nice case, what am I going to take? I'm going to consider big K a finite extension of these kinds of fields. So C double parentheses X, Y, right? So this is a finite extension. Okay, of course, what is this field? Well, this field comes as well with a natural ring, right? So this is just a fraction field of C double bracket X, Y, and these are Taylor series in 2 variables, right? And yeah, one last notation. So R, the equivalent of the R we got before, will just be, well, the integral closure. So you got a finite extension here, you got this nice ring, local ring. So now R will be a ring over this and will be just the integral closure of this ring in this field. Okay, So that is R and that is K. So now we got our R and our K. So the drawing looks actually quite similar. So I'm not going to draw R. I'm just going to draw the case of the trivial extension so that to give you an idea of the drawing, because otherwise it becomes uglier. But anyway, so what's the drawing for the trivial one? So spec of C, X, Y. What is this ring? Well, now you have to recall a bit of your algebraic geometry lessons. And this is just the local ring of the affine plane, C of XY without the double bracket, localized at 0, 0. Okay, so this is essentially, I'm going to put it here. So this is just A to C localized at 0, 0 at the origin. Okay, so how does the drawing look like? Well, once again, I got a big fat point here. That is just a generic point of this ring here. So that is essentially our big K. I had a whole bunch of one-dimensional points, okay, or codimension one if you want. And I got a teeny tiny point here, the local point that I'm going to put it in red. So this is 0, 0, okay? And so these guys over here, these one-dimensional points are essentially curves, plane curves, of course. These are the curves inside the affine plane going through 0, 0. That's what you get when you localize. Just curves going through 0, 0 and the point 0, 0. And where's the curve? Where are the valuations? What would correspond to the curve of the last case? Well, here you get a curve. So this is the curve. This is a one-dimensional scheme. Once I take out the 0, 0, this local point over here, I do get an actual curve. It's a one-dimensional scheme that has K as its field of functions. And so these guys are going to give me valuations. And this really, really, really looks like the classical case. Okay? So I'm going to get, once again, two types of valuations. So once again, so omega would correspond to valuations given by points in the curve, okay, right here, okay. And so what is omega 0? Well, omega 0, it's a bigger set. And what about him? Well, yeah. What do? Well, you take the fiber C0, that would be whatever lies above this guy, okay? And may I recall you that here you get a finite extension, so R will be lying above this. So you will have a curve over this curve, and you will have something really weird over 0, 0. And that's your closed fiber, okay? So that's C0, so it's just spec R times 0, 0 over C, okay? And yeah, so once again, same story. Again, this is singular in general. So you get a desingularize, and once you desingularize, you get irreducible components. Let me write that down. So desingularize and get irreducible components, which get new valuations. That's essentially it, okay? I told you this case was less nice. But anyway, that's what it is. There's nothing you can do. So these new valuations would be omega 0 minus omega. So yeah, and omega 0 is the whole set of valuations you got now to look at. Okay, so that's the two cases, the nice case, the less nice case. Let me tell you now some properties. I mean, what do they actually share with global fields, with classic global fields? We do have valuations, great. Now we can start asking the classical questions. So let me list some properties here. Oh, sorry. Properties of these fields, okay? So let me start of course, with the one I care a lot about, which is the Brauer-Manin theorem. So class field theory. Okay, what about that? Well, you do get, actually, you can, well, you always have a map from Brauer K to the direct sum of the Brauer KV. Here I'm going to put omega, careful, I'm not taking the whole bunch of places, I'm just taking the classical ones. And you can still get local class field theory and get maps to Q mod Z, and you can sum them up and take local invariance. And Brauer K will give 0 here. You get a reciprocity law. And actually, this complex is exact. And this, of course, will be surjective. So you almost got your Brauer-Manin theorem. Problem, there's a kernel. Okay, so here there's a huge, a priori, it depends on the field, of course. There's a huge divisible group. Typically, it's a direct sum of a finite amount of copies of Q mod Z. So something really weird, okay? And who controls this? Well, actually, the closed fiber. If you know the combinatorics and the genus of the curves that are on the closed fiber, you can actually control the co-rank of this divisible group. So you get information. So whatever information you lose when you go from here to there, you can recover it by looking at these new valuations. So actually, that's the good news. You can also get something like this. You can actually inject Brauer K into a direct sum of Brauer KVs if, instead of omega, you take omega 0. That's the point. Problem, I do not get Q mod Z here. I get a weird sum of Q mod Z's, and yeah, it's more difficult to track what you're doing when you're working with these exact sequence here. So yeah, that's a bit of a problem, but okay. So somehow, if you take into account these new places, you got yourself some nice Brauer-Manin-like theorem. So that's one of the first results you want to generalize. Another one that is really interesting and that it's really important in the context of homogeneous spaces is Poitou-Tate duality. Okay, so what is this duality? Oh my God, I'm writing really, really bad today. Sorry. So Poitou-Tate duality, what is this all about? So, well, Poitou-Tate duality can be stated for groups of multiplicative type in all generality, so finite groups, for instance, and tori. Let me just state it for tori here. So T at K torus, T hat will be its character module, so it's a Galois module. So I'm going to take the homomorphisms over K bar from T bar, so I go to the algebraic closure, to GM. So this guy is a nice finally generated torsion-free group with a Galois action. So given this, you can actually define the Tate-Shafarevich groups, either T or T hat, you can do it for both. Huh? So you define Sha-I of K-A for any A, either T or T hat, as, well, just the kernel of the natural map that goes from the ith Galois cohomology to the product of the local Galois cohomologies, okay? So of course, once again, I'm defining the classical Tate-Shafarevich group, so I'm going to take the classical set of places. So I'm just going to put omega here. So if I want to add more places so that I get a smaller Tate-Shafarevich group, I can put a 0 here, right? And then I'll add a 0 here, okay? So I got two types of Tate-Shafarevich groups, Sha-I and Sha-I 0, right? And yeah, once again, you gotta be careful which one you're using. So what do we know for, what is Poitou-Tate duality? Let me recall what Poitou-Tate duality is. So in the classical setting, over number fields or over global fields in positive characteristic, you got the SHA-1, so the first Tate-Shafarevich group of T has a natural pairing with the second Tate-Shafarevich group of T hat. And this goes to Q mod Z, and it's a perfect pairing. That's Poitou-Tate duality. And you get the same thing for, well, the other way around. So T hat times SHA-2 of KT. You also got a nice duality that it's a perfect pairing. These four guys are finite groups, so that's very important. And now, yeah, you can ask yourself, do I get these for these weird fields, these new geometric fields? Well, the answer is yes, but no. Okay, what do we get and what we don't get? You still have these guys defined. You can still define the pairings. These two will be finite, but these two won't be finite in general. So what you have to do to get a perfect pairing is actually put a huge bar here. And I'm going to define right here what a bar is. So here A bar will be A, and you mod out the maximal divisible subgroup. So yeah, these guys, these Tate-Shafarevich groups on the second degree turn out to be huge, like really infinite. They have a whole amount of divisible elements going on there, and they are really ugly. You have to mod them out, and then you can actually get a nice pairing. Let me remind you that I'm not putting any zero here, so I'm using the classical set of places. If I put a zero, there's no duality whatsoever. No Poitou-Tate duality, nothing you can do about it, okay? Because you can actually prove that SHA-1, 0 can be trivial and SHA-2, 0 will not, so yeah, there's nothing you can do, essentially. Bad news in that sense. But at least if you take the classical set of places, you're good to go. You have something that is close to Poitou-Tate duality. So let me just make a small remark on the Brauer-Hasenether theorem before. Recall that the Brauer group is just H2 of KGM, so it's a torus. So you can interpret this result on the Brauer group in this new context. So the sequence I had here that tells you this thing can have a kernel and can be divisible, it's actually telling you that it's equivalent to telling you that the SHA-2 of GN can be non-trivial. That's essentially what it's telling you. So over number fields, this guy is always trivial. That's the Brauer-Hasenether theorem. And over these fields, it's not, and it's a divisible group. Okay, so that's bad news. Now the good news is that SHA-2, 0 will be trivial, always. Okay, so that's why, once again, if you add new places, you get a certain control on that. That's, once again, what I told you about Brauer-Hasenether. If I add the new places, well, actually I get injectivity. So that's kind of saving a little bit of the information. So one last property I want to mention, it's absolutely of no use here, but just to make you understand how these fields are different from the classical setting, is that there's no analog, absolutely no analog of the Chebotarev density theorem. Okay. Really, you can have extensions that, for instance, give you trivial extensions like literally in every place, even if you consider these new places. Even if you consider any new place that you can actually get with any module, there are extensions, global extensions, that give you 0 locally everywhere. Okay, so having a little bit of expertise with Galois homology, you can actually say that in the following fashion. It's essentially the same thing, it's equivalent. It's just saying that SHA-2 KZ can be non-trivial. And actually, even SHA-2 0 KZ. So how do you realize this? SHA-2 KZ, if you take the classical exact sequence with Z and Q mod Z on the other side, you see that this guy is essentially SHA-1 of K with values in Q mod Z. And that's essentially classifying cyclic extensions that are trivial locally everywhere. Okay? So yeah, those guys exist. And this guy is this guy is actually divisible, as I told you before. I mean, they have a huge divisible subgroup. So you have a whole bunch of families of extensions that are locally trivial and that are non-trivial. This is just too much of a bad news for these fields. But anyway, yeah, so that's all the bad news. But I'm telling you, I'm not going to use these for now. Yeah, so one last remark before I get to the last part of the talk. Well, the Brauer-Manin exact sequence that I gave you before tells you that you can define a Brauer-Manin obstruction. Okay, so now you can start, now that I had all these nice properties of these new fields, I can start asking about local global principles for rational points over varieties over these fields. And I can start asking about Brauer-Manin obstructions to these local global principle. Okay, so this is the last part of the talk. So local global principles for homogeneous spaces over these new fields. Okay, so yeah, I'm a little bit late, but I think it should be fine. Okay, so here, yeah, let me then I'll try to tell you quickly what has been done with respect to these two fields that I just defined, the nice case and the less nice case. There's a whole bunch of other types of fields that people have studied. For instance, you can study function fields of curves over p-adic fields. Instead of the Laurent series that I took, you can change that by QP and study that. And there are nice results in that direction too. But okay, so let me just give you what is known in these two kinds of fields. So let us start, like the first story I told you, with principal homogeneous spaces. Okay, so this is a theorem that it's already stated, it's already known. So let K be either of the two cases above, okay? And let G be a connected linear K group, okay? Oh, sorry. Linear K group, and let X be a principal homogeneous space, so a torsor of G, okay? Then what you can prove is that the Brauer-Manin obstruction to the local global principle is the only obstruction. So just like Saint-Sucre did, you can take just locally constant classes in the Brauer group, and you can prove that if this thing is non-empty, then you got yourself a rational point. Okay. Yeah, a nice remark about this. No, sorry, before the remark, actually, let me just say who did this. Yeah, this is a result by Colliot-Hélène and Harari. This is in, wait a second, this is in the nice case. And in the ugly case, so the less nice case, it was also proven, same result, same hypothesis, but by Izquierdo. Essentially, what you had to do is do all over again the whole Brauer-Manin and Poitou-Tate and etc. Then the results are actually formal. So what Izquierdo did is actually find all those properties that I just showed you for the less nice case. Okay. So and now the remark that I wanted to state. Here. The Adels are with respect to omega, because recall, we have two kinds of sets. We had omega and omega 0, so I can define two types of Adels. So what it's telling you, this result is that, at least for torsors, things are really nice. You just take the classical set of places, the ones that actually are the analog of the classical case, and you get the same result with the same Brauer group, with the same subgroup of the Brauer group, so everything's fine. Okay, and this is where Izquierdo and myself come in. So this is the result that I wanted to present you. So if you want more details about this, you can talk to me later after the talk. So what about, so this is Borovoy's result in the classical case. What about connected or abelian stabilizers? Okay, So yeah, this year we started to work with Izquierdo on this question, and actually, well, things go wrong. That's what we got. So this is Izquierdo and myself. It's not yet on the archive, but it will soon be. I mean, we're writing down the introduction and that kind of things. The result is complete. So there are homogeneous spaces. Homogeneous spaces of, of SLN, so really nice group, already SLN with nice stabilizers, so toric stabilizers, so just a billion stabilizers in particular, a billion and connected, such that. So first of all, you got a non-trivial Brauer-Manin set, okay? So you can take the whole Brauer group, not just the locally constant things, just like really everything you can imagine from the Brauer group, and you get a non-empty set. So you get adelic points that are orthogonal to that. Here with respect to omega, actually. Why with respect to omega? Because well, let me say it this way. Actually, you cannot define a Brauer-Manin abstraction with respect to omega 0 for technical reasons. But you say, hey, I can actually create counterexamples easily if I get these, but I do not have a local point at a place from omega 0, but a new place. Well, just add this hypothesis. Put rational points, like local points, on every other place. So for every v in omega 0, add them, no problem, yet no rational point. Okay, so that's the result. Things go really wrong. And let me just give you the key ingredient of this thing, just to give you the name. So when you got X, a homogeneous space of SLN with, yeah, I want to say a billion stabilizer. This is the case, we have tori, so that's okay. With a billion stabilizers, actually, you can associate to that a class, eta sub X, that lives in some second cohomology group, Galois cohomology group, H2KS, that is called the Springer class. So this Springer is Tony Albert Springer, the one of the linear algebraic group's book, okay? Not the one that publishes a lot of books. Okay, and here S is a K-form of a stabilizer, okay? Because when you get a homogeneous space in general, if you do not know that you have a rational point, you must take a geometric point over K bar, then you get a stabilizer over K bar, and you got to make it descend to a K group. And you can do that if it's a billion. So if it's a billion, you can do that. You get a K form, and you get a class here. And the nice thing about this class is that for any field, you will get a rational point over L if and only if this class is 0 in H2KS. So giving yourself a homogeneous space that has points locally everywhere is essentially giving yourself a point class in SHA2, in the second Tate-Shafarevich group of this stabilizer S. So that is how you relate Brauer-Manin with Poitou-Tate. Okay, and that's how you start mixing them. So the recipe now, I'm not going to write it down. The recipe is find a torus that has a non-trivial. So you want a torus with SHA2KS0 non-trivial. So S such that you get this property. That's the first thing you got to do. You take a class in there, and you construct a homogeneous space of SLN that has that Springer class. So there you need a whole bunch of technical tools that we developed with Cyril Demarche last year, but it can be done. And then the difficult part is you got to make sure that these guys are, so there you got this and this, but you got to make sure that they are orthogonal to the Brauer group. And that's the really, really difficult part. So you got to make sure that your alpha in here, you got an alpha in here, has to be divisible when I look at it in SHA-2, okay? Recall that this is a smaller Tate average group than this one because I'm taking more places. So this is a subgroup of this. And when I look alpha in here, well, it has to be divisible so that Poitou-Tate duality will not see it. Hence, the Brauer-Manin abstraction will not see it. Hence, you get points that are orthogonal to the Brauer group. That's the recipe. That's the main idea of the results. And as a last remark, I just want to say that we do have stronger abstractions that explain everything. So they are the only abstraction to the local global principle for these kinds of homogeneous spaces. So homogeneous spaces with connected stabilizers or abelian stabilizers, we can explain them, but we had to develop stronger abstractions than the Brauer-Manin abstraction because things go wrong in that case. And having said that, I'll stop here. Thank you very much.
Okay, thank you, Giancarlo. Okay, are there questions for Giancarlo?
Is this one of the questions because you reduce it in a previous paper to SLN? One of those problems that can reduce further to SL2 with Lie theory, or?
Not really, because actually in this kind of context, the n in SLN is irrelevant in the sense that you can change it one for the other with no problem. But you have to keep track of the stabilizer. So you can change the n as long as you can plug your stabilizer into SLN. And you cannot plug any group into SL2. So the final answer would be no. Okay, so that's the problem. I mean, you can change to SLN as long as you can, to a specific n, as long as you can plug your stabilizers into that SLN. So if your stabilizer is isomorphic to a subgroup of SL2, you can, because the constructions are explicit. So if you give yourself a homogeneous space, you look at the stabilizer and you can plug it into SL2, you follow the constructions done in this paper by Demarche and myself, and you get a homogeneous space of SL2. But that's the point. I mean, you gotta be able to plug your stabilizer in there. So for instance, if I give you a torus of dimension 3, well, you can't. You can't plug it into SL2, so it wouldn't work. So in general, the answer is no. Yeah, otherwise it would be really nicer to tackle this problem. That's the point. Yeah.
So you can see it with the stabilizers that.
Yeah. Everything depends on the stabilizer. That's the lesson you learn immediately when you start studying these things. All the information is in the stabilizer. The ambient group, the one that acts, has some information, but you can quickly plug it into the stabilizer and just forget about that group and change it into SLN. And SLN has almost no information somehow. All the information is in the stabilizer.
Okay. Are there more questions or comments? Okay, if there are no more questions, we thank the speaker again.